Welcome to the Roboticist Chronicles, an ARC Specialties podcast, where we get into the nuts and bolts of robots, automation, and the implications of an evolving machine workforce.
Hello, this is Dan Alford. You're listening to the Roboticist Chronicles. We're reporting from the Offshore Technology Conference in Houston, Texas, early May 2023. I'm standing outside right now with a friend of mine. Bryan, you got a booth here too. We're kind of out of our place, aren't we? We're not oil field guys.
No, we're not, but we kind of make the last yard possible.
Yeah, so there's only 3 welding companies here: ARC Specialties, Lincoln Electric,
yeah.
And there's a pipeline company here.
Okay.
But what I've found that this show is great for me because all my customers have booths, and also there's a lot of activity. There's a lot of money flowing through the oil field right about now with oil at $80 a barrel. So it's working out well for us.
Yep. The show this year is definitely better than it was last year. Definitely getting better than what it's been since COVID.
Oh yeah, we filled it all the way from halls A to E.
Yep.
And it's almost like the old days. Now, back in the old days, you'd go across the parking lot here and they would have helicopters to buy and drill ships and other things, but it's getting back.
It's getting back. I think the thing that's interesting is you're seeing truly people from all around the world that are coming back to the show.
Oh yeah, there's pavilions from every country in the world here. This is a truly international industry.
It is.
But a lot of the technology comes right here from Houston. But I want to go in the booth, back to your booth, and show what you're doing, because y'all are doing some clever stuff on building these structures that are going offshore.
We are. We're working on advanced additive manufacturing solutions for the future of offshore wind and offshore oil and gas platforms.
And this is something I worked on way back in the early 80s, was jackup rigs. And so you have a couple of different technologies that are useful for building these offshore structures.
Yep.
Let's go back there and take a look.
Let's go see it.
Let's go.
Thank you.
So now we're inside the hall at the Offshore Technology Conference. We're in the Lincoln booth, and this piece of equipment caught my eye. What is this?
This is a very good representation of a TKY node. And TKY nodes are very common to the offshore industry, specifically for jacket platforms.
And if you rewind back to the early 80s, I was building jackup rigs for the Savad Offshore company, and this is the exact joint we used for all of the joints. So this looks very familiar to me. So the problem we had was we had to cut all these joints by hand. Y'all still doing that?
Hopefully not. No, there's more advanced solutions like that. So we have a company, Vernon, or a solution with Vernon tool that actually makes that cut. But what you said is most important is that since 1950, the welding really has not evolved. The processes have changed. There's been some increases in certain types of efficiency, but at the end of the day, you're still stuck in 1950.
Yep, and so the way we were doing it was with dual shield flux core.
Yeah.
Back in the day.
Yeah, there's 2 options. So one is gas shielded flux core, the other is self-shielded flux core. And it just comes down to the environmental conditions. But I would say predominantly in the world, gas shield is absolutely the #1 go-to choice.
Yeah, that's what we did.
Yeah.
But I remember we had a pipe profiling machine, much like this, except we couldn't do the beveling. And so we spent weeks developing an automatic bevel angle machine. Looks like you guys got that under control.
We do. And the thing that's interesting, though, is well planned out as all these cuts may be, all pipes are not round.
No pipes are round.
Pardon me?
No pipes are round.
No pipes are round. And as a result of that, you'll notice as you come around different transitions, you have excessively large gaps. And that becomes a real challenge because the amount of welding time that the customer has to spend on this is exponentially higher because the weld volume has to increase that much more to cover that gap. So this is an example really for offshore oil and gas platforms where we're really only welding from the outside. On an offshore wind tower jacket, we're welding on the inside.
Because the pipes are bigger?
No, we're welding because they're dynamically loaded. And they're dynamically loaded because of the turbine and tower that's on them spinning. That creates a different twisting effect to the whole foundation. And so those welds actually have to be done in short stubs and welded on the inside and welded on the outside. So effectively the jacket is welded almost twice in order to deal with that situation. These oil and gas platforms are generally considered statically loaded, so the load on top of them is not moving. And so as a result of that, they only weld on the outside.
So you're trying to improve that underbead condition.
Exactly. So in traditional offshore fabrication, we want to optimize the cut as best as we can, optimize the process. Whatever we can do to take the torch out of the welder's hand to increase the amount of operating factor, amount of time that they could weld. But the reality is, a TKY node as it is, the best craftsmen in the world are the welders that you have typically doing these, because these are the most difficult, and they're also one of the most inspected parts on the whole jacket, because of the critical nature of the joints and the connections to survive the loading conditions that they have. So,
and this is all high strength, low alloy.
yeah, it's not actually not super high strength material. So in the European system, it'd be like S355 to 460. So say 50 to 70 KSI yield type of material. You don't get much higher strength than that. Even in the jackup rigs, if you're familiar with jackup rigs, you have typically 690 steel for the main leg construction, but the pipes and braces that go between that are still only like X52. So it's high strength to low strength. And you still have the same issue. You still have these nodal connections that the world's been trying to fix since 1950.
So this is like much better than what I was having to deal with in the 80s. But on the other side of the booth, you got something that's radically different.
The other side of the booth will show you something that's kind of a game changer for the future.
Right.
But it is the future. It's how we're going to use technology to solve problems that haven't been able to be solved in, what, almost 6 decades now.
Indeed.
I didn't know you were that old, though.
Oh, I am.
You said 1950?
No. In the 70s, late 70s,
okay.
early 80s.
Okay. Because you look pretty good if you're that old.
Yeah. Any other thing on this?
I don't think so.
Let's go across the way.
All right, let's do that.
So now on the other side of the booth, this is a radical departure from the traditional technology. Tell us what you got.
So what you're seeing here is potentially the future for how jacket fabrication might look. What we actually have here, the silver part here, is actually 3D printed wire additive manufacturing.
Nothing but welding.
Just what it's welding.
Yeah.
You know, we can call it wham, we can call it bam, we can call it whatever you want, but at the end of the day, it's welding.
But this, you started out with a solid pipe.
Exactly. So we got smart and said, hey, if we want to print features and that meet a specific need, we don't necessarily have to print everything. We can start from a base material and then build off of that. So essentially what happens here is you take a design and you slice it into lots of different parts and pieces. And that software that we have actually takes that and then path plans how to print this in the most optimized manner over a period of hours or days or weeks or whatever has to happen.
So these are industrial robots with welding systems.
These are industrial robots with welding systems with integrated positioners, and they are coordinating the motion to optimize where they print, what plane they're printing in order to get the best feature. So.
And I see you've kind of changed the design. It's not just 3 pipes together. You've actually added some, in effect, gussets.
Exactly. So what's different about additive manufacturing, regardless of what the application is what we do with additive is we do what you cannot do with conventional pipe or plate.
Why not? You might as well optimize what you've got going.
Exactly. So what that means is inside of something like this, there can be internal features. The thickness from the bottom is not uniform necessarily with the top. And so what we do working with customers, as an example, in the offshore wind industry, is think about how do we optimize the whole design in order to improve the fatigue performance of this connection. And if we can improve the fatigue performance, we can actually potentially lightweight the whole structure. And we can also deliver a completed part ready for final assembly. What that means, big picture, is if we can develop this and commercialize this technology for that industry, roughly 60% of the welding done in the field goes away.
And it's the hard welding.
And it's the hardest of the hard. Yeah, absolutely. So,
particularly if you go to lap joints.
Yeah. So this has been a project for us for quite a number of years, and we've gotten to the point where we're printing to scale parts. We're working with partners like Stress Engineering.
Right here, right
down there, and they have a part down there as well. And we basically are working on the roadmap to industry acceptance. So if you look at the TRL levels of 1 to 9, and 1 is you and I had an idea on a napkin, that's a 1, and a 9 is fully commercialized, we're at a solid 6. So
I might give you a 7.
Or a 7. But we do operate the largest manufacturing, wire additive manufacturing in the world, actually, in Cleveland, Ohio.
In Cleveland, Ohio.
Yes.
How many robots do you have running? Is that a secret?
No, it's not a secret. I think there's 22.
22.
Yeah.
I think it's clever that you're doing variable wall thickness, because that's exactly how they build some of the most efficient structures in the world. They're called racing bicycles. And, and the tubing is thicker on the ends for a reason.
Yeah.
So back, in the old days, we'd have to compromise. You'd have to have the wall thickness constant down the whole pipe, because that's how pipe is made. But, so is this a fatigue problem, having all of these?
So that's very interesting, and if we can actually continue this series, we'll go down to stress.
Why not?
We'll talk about that. But surprisingly, in the work that we've done so far, we've done smooth ID and OD,
right?
And we've done smooth OD and nothing machined on the ID, and the results still exceed the DNV Class C weld for fatigue performance.
That's all you need.
We don't know why.
No, I can't explain that.
I can't explain that one.
So, is there an advantage to machining it, though? Do you see an increased fatigue life or not? You say it passes, but...
We don't know to what extent we have to machine. One of the things about machining that is a consideration is you're going to have to machine in order to do some type of inspection. So if people are hung up on phased array or some form of ultrasonics...
that's hard to read.
You can't read on that, right? You can x-ray it, but you can't necessarily...
But then you still have to ignore all the lines.
Yeah, you still have to... You're going to get too much noise in there.
Sounds like you need to invent a new technology.
We probably need to invent a new technology. We do have the capability to machine these perfectly baby smooth.
Right. But it's not necessary.
We would hope not, and especially on the inside. That would be the biggest challenge that we would probably get into. But
well, this is excellent. I see a lot of people doing additive, but I don't see a lot of real parts going into the real world. This gives me hope.
Yeah, this gives us hope too. So this is, realistically on the projects and opportunities with the global customers that we're talking to right now, we're one step closer to reality than we were 4 or 5 years ago in a big way.
What tensile strength do you feel comfortable with?
This is just welded with an ER70 S6 wire.
70 KSI tensile.
Yeah.
But how far will you push this technology? 80, 90, stop me when I'm close.
We print all types of materials. So we printed materials as strong as Invar. So Invar is a super, super hard tool steel. We print nickel. We printed stainlesses.
In the oil field, we use a lot of HY100 though. How will you?
Yeah, there's projects for that. So that's HY100 is very interesting to the naval industry.
Right.
And also pipeline people would be interested in strengths like that. So. And
you're willing to tackle HY?
We're willing to tackle anything to where it makes sense for the customer and for us as a business. So.
Gotcha. Well, maybe we need to go to the stress booth and look at the your fatigue specimens.
Okay, let's go do that.
Very good. All right, so I asked the question about the fatigue life of this material due to all of these ridges. And fortunately, the guys that are actually doing the fatigue testing are old friends of mine. So we got Pat Boster here with Stress Engineering. I'm gonna let you guys talk about what you've done on this.
Yeah, so Pat, we had a chance to see the original fabrication of how nodes were made, and we looked at the additive 3D printed node, and we talked about, does it really matter on the inside or the outside? And what we were talking about is the results that you guys have seen, and maybe you can explain a little bit to the audience about what you saw so far.
Sure. Stress Engineering has a history of running full-scale resonant fatigue type testing. And when I say full-scale resonant fatigue testing, in the Gulf of Mexico, that's happened from the ocean surface to the floor is exposed to resonant fatigue from VIV, vortex-induced vibration, from current simply passing passes, hitting natural resonant frequency and causing a vibration of the pipe. And that causes fatigue damage. So industry has developed a technique to evaluate tubular materials with respect to its response to a given condition where you hit the natural frequency and it gets exposed to fatigue damage. And so this is the gold standard for our industry. So subsea wellhead housings that produce hydrocarbons routinely get an E or an F2 class DNV rating for fatigue testing. So we thought, what would the additive portion be? So Lincoln is endeavoring to make a large complex configuration, and we've gone to a simplified version to get the baseline on a tubular section. Lincoln made a series of these tubular sections, 2 feet in length. We welded those to X65 pipe, The AM is very weldable, so we welded it, did a simple ASME Section 9 weld qualification, put a 2-foot piece in there. And in advance of that, what we do is we use, to recognize the difference in these ridges or these bead placements, we're concerned about the stress concentrations in these localized areas on the OD and on the ID. So what we did was we used 3D metrology to capture what the OD looks like and a laser scan on the board to see what the ID was. These are then identified, put into the assembly, clocked in a specific way so we can go back as part of a root cause analysis when we test a failure. And so what this is a laser scan where this is the center line, and these are all these little bead profiles. So if you have 10 beads per inch or 5 beads per inch, you're going to see these highs and lows, which are stress concentrations. Then when we do the fatigue test, we cap off the end, we put 9,000 PSI internal pressure, 17 KSI is the stress, and about 27,000 Hertz, and we start getting resonant fatigue. We take an eccentric weight, and we accelerate the weight until we hit the natural frequency, and then it begins to vibrate like a skipping rope. And then we're able to characterize this. And so what we did was we took pipe to pipe to get baseline. We took the additive, we machined OD-ID to see what additive was, and then we machined OD and left ID. And what we found was all 3 samples met a C-class curve. That's gold standard. So for probably 30 years, over 3 decades, I've done high fatigue welding, high fatigue class welding in top tension risers and other catenary riser components. That's as good as it gets. So the AM part itself is no different than any other structure, but it can perform as well as any other structure as well. And where it actually failed was not even in the AM, it was actually in a construction weld. So going forward this year, instead of 2 feet, where we have bending, where we're doing the resonant fatigue, we've moved it to 5 feet, so we lower the stresses in the construction weld, and we're going to try to drive a failure in the additive part. Because so far to date, we've had no failures in the additive piece when we've conditioned it.
How do you explain that?
Exactly.
With respect, it's a good question, and so
Yeah.
I will tell you that, first of all, your question is driven by...
Don't tell them the secret sauce, though.
Well, the question is driven by the localized reinforcement in this area, right, and the stress concentrations, right? So is it so local that it doesn't have that abrupt change that you might have like in a node or something like this? Right. You know, that's where we have a stress concentration. We had, back in the old days and maybe now, you put a coin and a paper clip wire in there to make sure you have a re-entrant angle of 145 or greater. You familiar with that? No. So that large area created a stress concentration. It may be that these are so close you don't really have a concentration. So as it turns out, people that were back in the beginning that retired from stress engineering have been there 40 years ago plus. We actually are having a meeting this Friday. We're having the gray beards. I'm a gray beard. I've got more grayer beards than me coming in. And we're having a round table on these results. Because if you have a girth weld with a protrusion, it's going to fail there before it's going to fail in this bead. That protrusion creates a greater stress concentration than this minimal amount. Now, what could get you in trouble? What Lincoln or somebody like this does is they put 10 beads per inch. If you had 3 beads per inch, you would have a series of saw teeth that would most likely create a higher stress concentration.
This averages out.
This averages out more so. That's our belief. That's my hypothesis. So we are taking a harder look at that, but that seems to be the case. So if you were looking and doing a quality check, one visual would be, okay, he's got 5 beads per inch or 10 beads per inch qualified. I can go up and look at that and say that's probably going to perform in a similar manner.
Interesting. I'm just delighted to see Lincoln actually doing some testing. A lot of people do additive and they'll say, look at this shiny part, and say, I don't care. You know, what's fatigue life, what's tensile strength, what's the impact toughness.
So our role, we're independent. We're totally independent, and so what Bryan and I have spoken about and others, it's a material substitution in part. So we look at it as, okay, is this the right material? So our role is to be the go-between where we feel we should develop a functional spec. What's the function of the part? What's a technical spec? What should it meet or exceed to perform in its intended function? And then a product qualification. Because you can do AWS, ASTM, ASME, and you can qualify to a procedure, but is a product suitable? So what we do, and what Bryan's having us do, is we'll do this work, which is NDE type, but we'll also do DIC, digital image correlation. So what DIC, whereas before people put a strain gauge and it's got a 1/4 inch or thereabouts as a test, DIC is a speckled paint color, it's a paint, and we've got high-speed photography, and what it's doing while it's under load is actually seeing those little facets adjacent to each other moving, and as they do, high-speed photography is catching that subtle movement and translating that to strain. So what does that do for us? It does two things. One, we can validate the FEA model that we've developed, and secondly, it's going to highlight any anisotropy that we have.
Excellent.
So we can do an unusual configuration, whereas a strain gauge gets this, and we average and project, we can actually do the whole profile. And we do that with the tensile bars also. We do a standard test, and I can show you where we've done these, where you can actually see the beads themselves share the load. And so the DIC will actually show you that visibly with the strain fields. And I can show you that on my film. So it's applying known technology to a known process that's been around since 1941, that Lincoln has added the robotics, the automation, the power supplies, and the positioning to put this all together, and we're just adapting then other technology that we use in other areas of the industry for this.
When's it going offshore?
Hopefully sooner than later. That would be
What
good.
year?
I can't tell you what year yet.
It's going to be in our test lab in 2023.
Yeah.
Okay.
Yeah.
It is in our test lab and it's continuing.
But results are encouraging.
Oh, they're
very
beyond
solid.
encouraging, and that's why you got to start with some baseline. And I think the expertise of stress, everybody in the world that is involved in energy, oil and gas knows who they are, and the quality of the work that they do. And just having a baseline like this, doing this number of tests and getting such a good result has really got us excited, and that's why we're building bigger and bigger and bigger and bigger parts, and that's why we're getting interest from the industry, people at OTC and other places that say, hey, this could change the entire way that we think about designing, building, and installing jackets. Or even floaters. So this concept can also apply to floaters, because floaters have TKY connections too as well. So,
Everybody does.
yep.
There are challenges in finding people in the workspace that can make these high-tech welds, right?
Yeah.
And so this eliminates that. It accelerates things where you don't really have that demand on the guy on the beach trying to make that weld. Lincoln can make this in advance. We can inspect it. We know what it is. The other thing we're doing is we're doing ECAs, engineering critical assessments, whereas we can take this material, we can do CTO fracture toughness testing, we can characterize this so you don't have to just go with a standard industry acceptance criteria. You can actually use engineering analysis to determine the acceptance criteria of what you've just built. So you add engineering to it. The other thing we've added to this, which you'll really get a kick out of, is if you haven't already. So we use strain gauges and other sensors in here. So we're making what's called a smart node. And the smart node is we actually have data onboard data acquisition systems that we'll do during the qualification. Then this can go to the field, and so we'll be able to have real-time data. So when a hurricane or other event occurs, that we'll be able to tell the operator how his part is performed. And we've been using this in the Gulf of Mexico for quite some time. And what it does, it adds to design life, to design extension and life extension. So you design it for worst case scenario. If the material's not seen that and we've got a record of that, then it will help us. We can also plan our inspection cycles based on that. So we're making a smart node, not only is a more economical node for that and very technically suitable for this, but we'll be able to have intelligence in the node.
When are you going to incorporate this into bridges? That's what we need in America.
Well, yeah, so there's work.
It's available.
You know, every different industry has its, game-changing kind of idea like this that we see, and we are working on those. And I think shipbuilding is another industry, but definitely structural connections. So additive is just, you think about the revolutions that happened in our combined careers, this is something that's just going to, just take off, and
once we do it,
10, 20, 30 years from now, who knows what it's going to look like. But
yeah, it's a natural.
Yeah.
It's like a paper clip. Why didn't we always use that?
Exactly.
Why didn't we always do this?
Exactly.
We butter welded, we base metal build up for decades. I have.
Right.
This is just a little bit more to it.
Original additive. But if you say it's going to work, I believe you, Pat.
Thank you, sir. And we're here to validate it together because we're going to help our industry and our society.
So I hope you enjoyed today's episode of the Roboticist Chronicles. Arc Specialties and Lincoln Electric have been collaborating for many years, particularly on submerged arc and some of our welding processes. What I wanted to show today is if you think that welding is about sitting under a hood with sparks falling on your head, you're way wrong. It is one of the most dynamic and interesting industries you could possibly be in. I'd like to thank you, Bryan, for having us in here today.
Yeah, thank you, Dan, and congratulations to Arc Specialties, celebrating many, many decades of success.
Appreciate all your help.
Thank you.